Welcome to this presentation on modern Dart, mastery of version 3.x. Today, we are exploring what is truly a fundamental transformation in safety, expressiveness, and control within the Dart ecosystem. As we dive into this new era of development, we will focus on the core pillars that define modern Dart: sound null safety, records, pattern matching, and feature flags. Each of these advancements represents a significant leap forward, empowering us to write more robust, readable, and efficient code. Let's get started. Dart 3.x represents a fundamental shift in philosophy. It is more than just a routine update. It is a comprehensive transformation designed to reduce boilerplate and eliminate entire categories of bugs. This evolution is built upon three core pillars: safety, expressiveness, and flexibility. First, Dart is now fundamentally safer. With the implementation of sound null safety, the compiler acts as your primary line of defense. It identifies potential errors early, effectively preventing runtime crashes before the code is ever executed. Next, the language has become significantly more expressive. The introduction of patterns and records allows you to communicate intent concisely, removing the unnecessary verbosity often found in traditional object handling and making the codebase much more readable. Finally, we have ensured the language remains flexible. Feature flags provide an opt-in path to the future, allowing for safe experimentation with cutting-edge language evolutions without compromising the stability of your current environment. The compiler serves as your first line of defense in maintaining code integrity. A key concept in modern development is sound null safety. When a variable is explicitly typed as a non-nullable string, the compiler enforces a guarantee that it can never be null. As illustrated here, an attempt to assign a null value to such a variable is immediately identified as a compile time error. By catching these issues during the build process, we prevent null reference exceptions from occurring at runtime, which results in significantly more robust and reliable software. The Null Safety Toolkit provides a foundational set of rules and features for managing nullability in Dart. Looking at the syntax grid, we distinguish between different variable states. A standard declaration, such as string, is non-nullable, meaning it must be initialized and can never hold a null value. By adding a question mark, as in string question mark, we define a nullable type that can explicitly contain either a string or a null value. For situations where we need to tell the compiler a value is definitely present, the exclamation mark acts as a null assertion. Additionally, the late keyword allows for deferred initialization, promising the compiler that a variable will be set before it is ever accessed. A standout feature of this toolkit is flow analysis. As demonstrated in the code example, Dart's compiler is intelligent enough to track variable states through logical checks. When you perform a null check, such as if text not null, Dart automatically promotes the variable from string question mark to a non-nullable string within that specific block. This type promotion allows you to safely access properties like text.length without any additional syntax or compiler errors. Let's look at how Dart 3 simplifies bundling data by removing unnecessary boilerplate. Traditionally, if you wanted to group multiple pieces of information together, such as an item name and its price, you are required to define a dedicated class. As illustrated on the left, this old way involves writing a verbose class definition with final fields and a matching constructor, just to hold a simple pair of values. With the introduction of Dart 3, we now have records. Records are immutable aggregate types that allow you to bundle data using a much more concise syntax. On the right, you can see how we can achieve the same result with significantly less code. We can use positional records for quick groupings, or utilize named records for greater clarity. By specifying labels like item and price directly within the parentheses, the code remains self-documenting and readable without the overhead of a formal class structure. Pattern matching and destructuring allow you to unpack data directly from objects, lists, or records into variables in a single, concise step. First, let's examine records. In this example, a record containing the string John and the integer 25 is destructured into two local variables. As the diagram illustrates, the first element is assigned to the variable name and the second to age in a single operation. This functionality also extends to class instances. Given a user class with name and age properties, we can use an object pattern to extract these values into specific variables. By using the syntax var user name n age a equals user, we extract the property name into the variable n and the property age into the variable a. This powerful feature streamlines data handling and significantly improves code clarity. This slide illustrates the transition from traditional switch statements to modern switch expressions. On the left, we see the imperative approach, which is often verbose. It requires declaring a result variable beforehand and using explicit break keywords for every case to manage control flow. On the right, we see the functional style switch expression. This approach is significantly more concise and readable because it allows us to return a value directly. By utilizing the arrow syntax and a simple underscore wildcard for the default case, we eliminate unnecessary boilerplate and reduce visual clutter. Advanced control flow allows us to combine logical operators and custom conditions directly inside case patterns, making our code more expressive and concise. There are 3 primary techniques to achieve this. First, we have the logical OR operator, which allows a single case to match multiple specific values. For example, case 1 or 2 will trigger if the input matches either integer. Next, we can utilize relational operators to match values within a specific range. In the example provided, case greater than or equal to 10 and less than or equal to 20 efficiently handles any value between 10 and 20. Finally, we have guards, which use the when keyword to introduce custom Boolean logic. Here, case var n when n modulo 2 equals 0 ensures that the case only matches if the value is an even number. These advanced patterns provide a cleaner syntax for handling complex branching logic without the need for nested if statements. Sealed classes are a fundamental architectural tool in Dart that enforce complete handling of logic through a concept called exhaustiveness. When we define a class as sealed, such as the shape class shown here, we are explicitly informing the compiler that the list of its subclasses is fixed and known. In this hierarchy, square and circle are the only valid implementations of a shape. This constraint provides significant safety when writing conditional logic. As seen in the code example, when we use a switch expression to handle a shape object, the compiler can mathematically verify that all possible cases have been covered. Because the hierarchy is closed, a default case is unnecessary. The compiler effectively acts as a safety net, ensuring that every branch of our logic is accounted for. The true value of this approach becomes apparent during code maintenance. If we were to introduce a new subclass, like triangle, the compiler would immediately flag this switch expression as an error because it is no longer exhaustive. This forces us to update our implementation to handle the new type, preventing the kind of forgotten case bugs that often lead to runtime crashes in less restrictive architectures. To synthesize these concepts, let's look at how combining sealed classes, patterns, and null safety results in robust state management. This switch expression elegantly handles the various states of an operation. First, it matches the state type directly, as seen with the loading state. For the success state, we use object patterns to destructure the data and message properties immediately into local variables. Notice the use of a guard clause with the when keyword. This allows us to specify a more precise match for when a message is present, while the subsequent case handles the fallback. Finally, because the underlying result class is sealed, the compiler ensures exhaustiveness. This means we are required to handle the failure state, preventing common runtime errors by forcing us to account for every possible outcome at compile time. Let's look at deep JSON validation. Traditionally, verifying unknown JSON structures involves a series of nested type checks and null safety guards. With pattern matching, we can condense structure, type, and content validation into a single declarative line of code. In this example, we take an unknown JSON map and pass it through a specific pattern. This single if-case statement performs 4 critical validations simultaneously. First, it checks that the key user exists in the map. Second, it verifies that the associated value is a list. Third, it ensures the list contains exactly 2 items. And finally, it validates that both of those items are strings. If the incoming data matches the specific shape, the pattern automatically destructures the values and binds them to the local variables name and role. This approach eliminates verbose boilerplate code, making our data handling significantly safer and more readable. This slide demonstrates a practical synthesis of records and pattern matching in Dart, specifically for handling geolocation data. On the left, we define a function called getLocation that returns a named record containing two nullable doubles, latitude and longitude. Using a record here allows us to return multiple associated values easily, without the overhead of defining a custom class. On the right, we see how to consume this data efficiently using pattern matching within an if statement. The if case syntax allows us to destructure the record and perform type checks simultaneously. Crucially, as the annotation indicates, checking against the non-nullable double type acts as an implicit null check. If either field in the record is null, the pattern will not match, and the block will not execute. This ensures that inside the scope of the if block, both the latitude and longitude variables are guaranteed to be non-nullable, providing a safe and concise way to handle optional data. Opting into the future of a programming language involves utilizing feature flags and language experiments. These flags provide a mechanism for developers to test and provide feedback on language features that are still in active development, such as macros. It is important to remember that these are distinct from application-level A/B testing flags, as they focus specifically on the underlying language and compiler capabilities. There are two primary ways to enable these experiments. First, you can configure your project's analysis.options.yaml file by adding the Enable Experiment key under the Analysis section and listing the desired feature. Alternatively, you can enable an experiment during execution by passing the Enable Experiment flag to the command line, as demonstrated here with the Dart run command. Dart 3 introduces several features that can significantly improve code quality and maintainability. One key recommendation is to prefer switch expressions over traditional if-else chains. This leads to clearer, more linear mapping logic that is easier to read and maintain. For robust state management in architectures like Block or Qubit, utilize sealed classes. These provide exhaustiveness checking, ensuring that every possible state is explicitly handled at compile time. It is also important to trust Dart's advanced flow analysis. By minimizing the use of the null assertion bang operator, you allow the compiler to safely promote types for you after logical checks. Lastly, adopt records for temporary data groupings and as functional return values. This eliminates the need for defining single-use classes, keeping your codebase concise and efficient. Following these best practices will help you leverage the full potential of Dart 3. Dart 3.x fundamentally transforms the developer experience by shifting the technical burden from the programmer to the compiler. This evolution results in code that is inherently safer, more concise, and significantly easier to maintain over its lifecycle. By allowing the compiler to handle complex checks and structural optimizations, developers can focus on building features rather than managing boilerplate, truly enabling them to code less while doing more.